So what did we do last time? Beyond logistical nonsense, we started talking about kind of background on controlled dynamical systems, what dynamics look like in continuous time last time, right? Oh, by the way, I posted the YouTube video and the notes and stuff from last time like a couple hours ago, and I put a Piazza message out. Sorry, it took me longer than it should have. Generally, I'll try to do it like within a day, FYI. Okay, so we did that stuff. We talked about manipulator dynamics. We talked about equilibria. And we talked about stability and how to get at that with linearization and checking eigenvalues and this kind of thing. I should mention as a caveat, right, that notion of stability, there's many different definitions of stability. The one we talked about last time is sort of local stability, and also called asymptotic stability. And there's other versions of that that you might see. There are sort of broader versions of that. But that's sort of enough for us in here, I think, for the time being. Okay, so what are we going to do today? We are going to continue the dynamics crash course. So today will be the end of like dynamics crash course, and then next week will be optimization crash course. And then we'll have, basically dynamics and optimization are the key ingredients for optimal control. That's basically what it is, right? And sticking those together. So hopefully by the end of next week, we'll have a handle on the background stuff. So today we're going to do basically how to get all of this dynamic stuff into a computer. So we talked about continuous ODEs last time, all this nice F equals MA stuff. But then what we really need to do is start talking about algorithms, both like controls and optimization, with this stuff, is figure out how to take those continuous time ODEs and map them into discrete time maps for simulating stuff and running things in a computer, right? So we'll call it discrete time simulation, say. By the way, I found it is extremely common for there to be, among computer scientists, there's this hang up where people sort of like differentiate between the word model and the word simulator. These are the same thing, and they will be, those words are interchangeable as far as we're concerned in here. I think like in the RL community, there's some hang up on this. They'll draw some distinction that I frankly don't understand. If anyone can give me their personal take on the difference between those two things, I'd be curious to hear it. But as far as we're concerned, model and simulator are the same thing. Cool. And then we're going to do more stability stuff kind of in discrete time, and also as part of this discussion on discretizing ODEs and simulating them. Because there are demons lurking in there. If anyone has done this before, you'll know what I'm talking about. We're going to sort of like pull the lid back on some of this and show you where the demons lurk today. Okay, the punchline on that is never trust your simulator. Always be skeptical of your simulator. All right, so the kind of the motivation for what we're going to talk about, as everyone who's taken a course on differential equations will know, in general, we cannot solve x dot equals f of x for x of t. We can basically only do this for the very special case of linear differential equations. If it's a nonlinear ODE, which is everything interesting, from robots to spacecraft to airplanes to whatever you care about, it's nonlinear and there's no way of solving that thing analytically, right? So then we got to get it into a computer. And also as part of that, we need to, computers can't deal with, continuous things like continuous functions. We need to represent this somehow with discrete values in a computer, right? And by discrete values, I mean like discrete time steps or whatever, right? We can't have this like infinite dimensional continuous time thing in our computer, right? Okay, so, and then as a kind of an aside that is interesting that we will get into later, there's certain sense in which discrete time models or discrete time mappings are actually like more general and can express things that these continuous ODEs can't because of certain smoothness assumptions baked into just the very idea of a differential equation. This comes up when we get into like contact dynamics where you have these discontinuous impact things. Those can't be written down as ODEs. But they can be written down as sort of these discrete time maps, which is kind of interesting. All right. Yeah, I mean, that kind of goes along with the very idea of, impacts being non-differentiable, right? It's in the name, differential equation. So if x of t is non-differentiable, its derivative is not defined, I can't write down an ODE for it, right? At like a very basic level. Okay, cool. So discrete time stuff. Did something bad happen? Okay. Discrete time dynamics. So the first thing is there's kind of a few ways of writing these down. So we'll first talk about explicit discretizations, or the kind of explicit form of these things. So that's where you have an equation for xk plus 1 as a function of, and so just for today, to differentiate between the continuous f that we talked about last time, we're going to put a little subscript d on this guy for discrete time. So we have xk, uk. So these are, right, discrete times. So we have some time step here. And we're going to have a function f sub d, discrete f, that eats x at the current time step, u at the current time step, and spits out x at the next time step, right? So this is an explicit discrete time model. The d subscript will be discrete for today. After today, we're not going to, basically everything will be discrete time after today. So we will drop the little d in the future. Okay, so that's, there are many, many ways of getting an explicit discretization like this. First thing we're going to talk about is the simplest one, which I'm sure pretty much everybody has seen before, which is explicit or forward Euler integration. Which looks like this. So you get xk, you just take the f, the continuous f, which gives you x dot, and you take a little step along the x dot direction of length h, which is your time step. So that looks like this. This h is your time step. I guess that doesn't need to be in quotes. And then, yeah, this whole thing is called, so this whole thing would be your FD now. And this is called forward Euler. Who's done this before? Hopefully like everybody, right? Okay, cool. Okay, so what we're going to do now is do this on our favorite nonlinear system, the pendulum from last time. So let's go check that out and see what happens. Okay, here's our Jupyter notebook. So I'm going to post code for all these things. I'll post these notebooks all the time. This is Julia. It looks pretty much like MATLAB, as long as you don't do anything fancy, and we will try to avoid doing fancy things. Things that it has that are better than MATLAB, it has a real package manager, which is amazing, with like versions and stuff. So that's what that top line is. The top line is using the package manager to, so these two files over here, this manifest file and project file, they have all the dependencies for the notebook with version numbers. So I'm just going to post this all on there. When you call this first line, it's calling the package manager, and it's telling it to install the exact same versions of all the dependencies that I'm using in this notebook. So there should be zero compatibility issues for all of you, which is fantastic. The only thing I'll mention here on the Julia side of things, For the class this semester, we're using the long-term support release of Julia, which is 1.6.7. There's a newer version, which is 1.8.5 is the current release. We're going to use the long-term support version because there are fewer issues. If anyone has a Mac, M1 Mac or whatever, this version is x86 and it runs fine in Rosetta. That's what I'm doing. So you should have no problem. Just install the like standard x86 build. It'll work. Don't do anything weird, basically, and everything should be cool, which is why we're using the LTS release and whatever. We don't have issues. So yeah, this is just packages I'm using. Linear algebra is obvious. PyPlot is the exact same, plotting library. It's matplotlib from Python, so it should be very familiar with most people. And then forward diff, which we'll use a ton in the class, is automatic differentiation. So I don't have to hand write derivatives, which is also fantastic. Yay, Julia. So there will be homework 0 actually is going to basically cover how to use forward diff and some of these things in some amount of detail for you guys. And that should be getting posted today also. Should be easy. Okay, so here's our pendulum dynamics that we wrote down last time with length equals 1, G 9.8, right? And that's it, right? Oh, we maybe didn't talk about this last time. The mass cancels out in these equations and doesn't matter. Yeah, probably most of you have seen this. Sorry, I should have mentioned that probably. But yeah, so here's what theta double dot is, right? I have m, ml squared, whatever. And if I divide through both sides, the m goes out away, right? So the only things that matter are G and L. But this is just the dynamics we wrote down last time, right? Where the state is theta double dot, and this function returns x dot, which is theta double dot, right? Cool. This is, yep.
How do you add this special here?
Oh yeah, that's fun. So Julia natively supports like basically all of LaTeX. So I can just write theta. You write / theta just like you would in LaTeX and hit tab, and it does anything you want, which is pretty sweet. So you can write your code. You can look like your math. You can, so yeah, like theta dot is / theta / dot tab. Yeah, renders the LaTeX, which is cool. You'll get the hang of it. It's not too hard. But otherwise, yeah, it basically looks like MATLAB. Like if you just write like that's how I started getting into this. I literally copy pasted my MATLAB code and fixed the handful of errors. So if you know MATLAB, this is very, very easy. Okay, cool. So there's my dynamics. This is my f, right? F of x from last time, continuous time. X here, x1, I'm pulling out the theta and theta dot explicitly. I evaluate theta double dot, and then x dot is theta double dot. Cool. Okay, so here's the forward Euler integration that we just wrote down. So I'm going to run this from, yeah, okay. What's it doing? It's going through the loop here, right? And here's, xk plus h times f of xk is xk plus 1. That's sort of what we just talked about, right? And now I'm going to go run this from an x naught that's like pretty close to the downward equilibrium, right? 0.1 radian, so like a few degrees, and I'm just going to let it swing passively under the dynamics. And let's run it. We're going to run it for 5 seconds with a time step of 0.1 seconds, so like 10 hertz. And we're just going to see what happens. Okay, and then plot this. What's happening there? What should happen there? So there's no damping. So I wrote down, just the original ODE, which should just intuitively, if there's no damping, there's no anything, it should just rock back and forth about that same initial angle forever, right? That's what it should do. What is it doing? It's getting bigger, right? It's blowing up. It's not damping, it's the opposite, right? You're getting energy increasing, right? Anyone have any thoughts on what's going on here? Yeah. That's a good, yeah. So this is very intuitive, right? So we're using some discretization, like it's definitely got some error associated with that approximation where we took a little step along, x dot. So maybe I need to make the time step bigger. So let's try running it at 100 hertz instead of 10 hertz. That's a very good idea. What happens there? It's a little better. Let's run this out for a longer amount of time though. Let's run it for 50 seconds instead of 5. It still blows up. You don't have any other thoughts on this? Yeah. Yeah, error accumulation is that's always going to happen. Absolutely. But there's something a little extra weird going on here associated with this blow up, right? Because error accumulation, that could do anything, right? And if the errors were random, you'd expect it to sort of average out to 0, right? Like if the errors were, say, pure random, uniformly distributed, and you did this over time, you would get something like a random walk or it average out in some sense. And that's not what's happening here, right? There's a very particular energy blow up behavior happening here. that's associated with like an instability, right? Yeah, what do you have?
Well, so we're taking, the tangent lines with the slope.
Yeah,
so we're always overshooting.
that's exactly right. Excellent. Yeah, I was going to draw that little cartoon in a minute, but that's awesome. That's like the key insight, right? So there's a very, very peculiar interaction here between the natural dynamics of this system, which are oscillatory, and the fact that you're always taking a linear approximation of the trajectory with this Euler integration. I'll draw the picture, don't worry, but you nailed it. Yeah, so you end up actually always overshooting, right? So you can imagine my sine wave is going up and I take a linear approximation. That linear approximation is going to always overshoot the sine curve. And so as I keep going and doing this, I'm always overshooting at every dip of the sine, right? Because a linear, there's like you can write this down formally, but that's the insight. Yeah, did anyone else have anything to add to this conversation? But yeah, awesome. Way to go. Okay, cool. So let's go write down some math now and look at this. But yeah, so the key takeaway message is it doesn't matter how small I make the time step here. I can make it arbitrarily small. I can go to 1,000 hertz. I can do whatever I want. 1,000 hertz is still doing this, right? All that happens is it basically delays the inevitable. It's going to push the blow up out farther in time. Yeah.
So can't we remove the positive part of the eigenvalue?
So there's something there. So what we're going to do now is go write down the eigenvalues of this thing and then think about that a little bit. So not exactly, but we'll get to what's going on in a little bit more detail and like show you what to do. Any other questions about anyone want to try anything else here? You don't believe me? All right, cool. So we'll go back to the math for a minute. So what did we do? We did, like L equals M equals 1. We did H equals, 0.1, 0.01. We did kilohertz, right? And it sort of always blows up no matter what you do. And then we kind of you actually nailed the intuitive answer to this, which no one's ever gotten before. So awesome. Have you seen this before, or did you just get that on the...
At some point, I tried to program in orbit simulator.
Yeah, same thing. It's anything oscillatory. You'll get this actually for that exact reason, right? Like orbit's the same deal. It's a periodic orbit. Yep. Okay, cool. So let's talk about stability of discrete time systems. So remember, and I think the overall message I'm trying to convey here is be careful, because whatever your continuous system does, when you discretize it, weird things can happen. And the discretization can introduce really gnarly systematic errors in the solutions that aren't physical, is the overall takeaway. But we'll get into some of the details. Okay, so from last time, in continuous time, we had this kind of eigenvalue result where we wanted the real parts of all the eigenvalues of the Jacobian matrix to have to be strictly negative, to be stable, right? And we talked about this marginal stability case where it was exactly 0, which is actually the thing we've got here, right? Which implies sort of bounded oscillations. Okay, so let's think about what is happening in discrete time. So when I go simulate this thing in discrete time for a long time, right? If you think about what's actually happening there in terms of the dynamics, the discrete dynamics, it's really an iterated map, right? Like if I simulate this for a bunch of time steps, I'm calling f of f of f of f of f of f of x, right? To go so many time steps in the future, right? So it's function composition of this FD, right? That's mapping me so many time steps in the future. So we got xn is f of f of f of blah, 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 lots of f's of the initial conditions, right? Something like that. So if I think about that sort of, iterated map, and I think about linearizing it, I get chain rule. I'm backpropping through that thing, right? So it's basically the Jacobian of FD times, just iterated through, right? So if I take this, if I linearize this about the initial condition x naught, right, about that initial point, then all the Jacobians are basically the same thing if I'm doing it like at an equilibrium. So then it's just that one Jacobian just chained together, right? So we're going to do that. So partial xn, partial x naught is really what we're after, right? So we're going to call remember we called A the partial f partial x last time, the dynamics Jacobian, right? So this we're going to do for today, A sub d for discrete. So this is A sub d to the nth power, right? It's just, yep. So this, okay, so if I want to simulate n steps of dynamics in discrete time, I got my discrete time dynamics and I just call it n times, right? And I call it on the output of last time. So it's an iterated math, right? So it's like f of x of, it's f of f of f of f of x, right? N times for n time steps, right? That makes sense? Cool. So then if I linearize through that, I just chain rule through all those function calls. And then it ends up being, you know, chain rule, right? So this is like, just take, yeah, so what I'm going to do here is I'm going to linearize about an equilibrium point. So if x naught is an equilibrium point, then it's just sitting there for all time, right? At that equilibrium point, right? So it's this fixed point, stable, blah, blah, blah. Like think about, so x naught here is like the pendulum hanging straight down, right? So if I call this n times, it's going to just sit there straight down because it's an equilibrium point. So then that x is the same for all of these n time steps. So then therefore the Jacobian is the same Jacobian for all n time steps. So then it's just a to the nth power, right? Does that make sense? Is everyone clear on that? Any other questions about this?
So it's only valid about equilibrium.
So this, you know, what I just wrote down is true always, but if it's not an equilibrium point, like if I'm doing this about some trajectory or something where x is changing it, then these Jacobians would each be evaluated at a different x, but the chain rule thing, you know, still applies, right? Okay, all good? Yeah, so for right now, we're talking about an equilibrium point though.
Like notation, it's the partial x, partial is, shouldn't that perhaps be like partial x and partial x at x naught? Or
yes, they're all evaluated at x naught in this case.
no, I get that. I mean on the left hand side.
On the left hand side.
Just notation.
Yeah, I don't know. So what I'm trying to get at there is I want partial of xn with respect to x naught, all the way on the right. I don't know. Yeah, I don't know. The notation's a little weird. I don't know if I'm open to suggestions. But is the idea clear?
Yeah.
Like I'm really trying to take partial of the output of this with respect to the initial input on all the way on the right hand side.
Respect to the initial state.
Yes. So this is the partial of the final state after n time steps with respect to the initial state at time 0, right? That's what that derivative is. And if I just go do that through that, you know, function composition, I just get chain ruled. And because it's an equilibrium point, it's sitting there for all the time steps. So all the Jacobians are evaluated at the same x. So that's just a to the n, right?
So won't it be n minus 1 and so on?
Yeah. I mean, it's, well, sorry, can you repeat that?
The denominator, won't it be dx n minus 1, dx n minus 2?
Oh yeah, as you go across, yes. But the point is here, because it's an equilibrium. So in general, you're absolutely right. Like if this was moving around and it was a trajectory that I was linearizing about, 100%. In this particular case, those xk's are the same for all k because it's an equilibrium point. And so it's just going to sit there, right? Does that make sense?
Okay.
Yeah? Yeah, I'm sorry if this is not clear. We got a little screwed up there. So hopefully this is clear. Definitely stop me and interrupt me if this isn't making sense to you. Okay, cool. So is this clear to everybody now, what we're doing? Awesome. Okay, so now we're going to make the assumption here, which is kind of trivial and not important actually, but just for now to make life easy, we're going to assume that we've set our coordinates up so the equilibrium point is at x equals 0 at the origin. It's trivial to just shift this over by a constant. So like we usually assume this. So in, you know, x naught equals 0, basically at the origin. And so this is the case in the pendulum in particular, right? Theta equals 0 is this downward equilibrium. So we're in this situation already. And so if we think about what it means to be stable here, we're talking about, right, in this case, stability means if I perturb this thing a little bit from x naught, it you know, as I take the number of time steps to infinity, right, as I like run this simulation forward for like many, many time steps, it should converge back to x naught, right? Does that make sense to everybody? So if I think about the linearization, then what that's going to mean is any x naught has to converge back to 0, right? So if that's true for any x naught, so let's write that down. So I'm saying limit as k goes to infinity. If I'm using the linearize that dynamics, it means a, this discrete time a to the kth power times x naught has to equal 0 for all x naughts, right? Okay, so if that has to be true for all x naught, what can I say then about the A matrices? Yeah. Yeah, inside, strictly inside, right? Modulus. So another way of saying this, though, a sort of dumber way of saying this, you know, for me is like limit as k goes to infinity of just the A matrix, right? Has to equal 0. If it's got to be true for all x's, then it has to be true for the matrix that's multiplying x, trivially, right? Okay, so for that to be true, then like you nailed it, right? Then if this is always true, this says that the complex modulus or like norm, right, of the all the eigenvalues of this matrix have to be strictly less than 1 or inside the unit circle in the complex plane. That makes sense? So yeah, intuition is just like, as I take that iteration out to infinity, I'm just multiplying those A matrices together. If that like has to go to 0 for any x naught, it has to go to 0 for the matrix. And the way that, another way of saying that, like a to the n goes to 0 for large n, is that the eigenvalues, yeah.
Just to confirm, are we saying it goes to 0 because we set the coordinates as the origin to 0?
Yeah, so what ends up happening if it's not the origin is you just get a constant in there, offsetting it. And so there, the matrix condition actually is exactly the same. So what it would end up being is like a to the x plus constant c offset, you know, and so like the constant drops out when you like do this. So it's still the condition on the matrix eigenvalues is the same. Basically, we're just dropping this constant offset that doesn't matter. It's kind of making it the origin. Cool. Everybody cool with that? Any questions or thoughts on this? Okay, so now what we're going to do is do this calculation for the pendulum with forward Euler. Okay, so to be super explicit about this, here's what this looks like, right? Xk plus 1 equals xk plus h times f of xk. And this whole thing is our fd of xk. So now we're going to compute the Jacobian matrix. So this AD thing is partial of this fd with respect to xk. So I'm going to go ahead and just like linearize that thing, right? So that xk is going to turn into an identity, partial x, right? And then the other part is going to be h times the original Jacobian, you know, the original A Jacobian, right? The continuous dynamics. So if I kind of keep writing this out, expand it out a little bit, I'm going to get I plus h times, we wrote this thing, I think, yesterday, which is, you know, easy to do. Q over L cos theta, 0. Should write this a little bit. Cool. Everyone cool with that? So I'm not going to sit here and like compute eigenvalues of this thing. We're going to use the computer to do it. I'll just write down. So if I take the eigenvalues of this thing, using the numbers we just used in this simulation, so we're going to linearize this about, we're going to plug in theta equals 0. So that cos is going to be a 1. And we're going to use h equals 0.1, say, you know, the first thing we did. These eigenvalues are going to be 1 plus or minus 0.313 I, approximately. So what's the takeaway from this exercise then? This is most definitely unstable, right? So let's go, also h equals 0.1. Okay, let's go look at this. So now we're going to do something fun. We're going to go back to the the Jupyter notebook and pray that my computer doesn't barf again. Okay, so let's see. And now I'm gonna have to run a bunch of this stuff again. Because it crashed. Hopefully it still works. It's gonna think for a minute. I should have done this before while I was writing. Cool. Okay, so we're back to this. Let's go put it back to like the 10 hertz version just to check my math. 5 seconds. Otherwise, it just looks stupid. Cool. Okay, so here's my discrete time Jacobian that I just wrote down. Everyone agree that I did that right? Didn't do anything super dumb. I think I did that right. Cool. And then I'm just going to take the eigenvalues of that thing, evaluated at time step is 0.1 and at theta equals 0, right? So that's what we wrote down. So and yeah, what else we did? We did like 100 hertz. We can check it. It gets closer and closer, right? 1,000 hertz, but it's still always bigger than 1. So let's plot this. So what I'm going to do right now is plot these eigenvalues, their modulus, as a function of h while I vary h. And what ends up happening here is that it asymptotically approaches modulus 1 as h goes to infinity, but it never actually gets there. So the message here is that if I'm using forward Euler to simulate a pendulum, which is like a trivially simple system that we all kind of are familiar with, it will always blow up no matter what you do, no matter what finite time step you take. It will always blow up. There is no, it is beyond redemption. Anyone have any thoughts about this? Questions? Want to try anything else? So takeaway of the day, don't use forward Euler. It is bad for you. It's a bad thing. What else? Okay, yeah, cool. Any questions? Yeah. So this is basically doing that. Well, so the linearization is making that small angle approximation thing, right? But yeah, this particular blow up thing, this is kind of like an energy thing, right? There's like energy being added to the system. And it's a particular quirk of the forward Euler integration. And yeah, let's go draw that picture that you told us about. Where did I? Yeah, let's do this. It's still working. Hooray. So what did we just do? We did this thing. We did versus h, and yeah, basically only like asymptotically approaches being stable. So that's not great. And let's see. The intuition here from like a physical perspective is if I kind of think about what's going on, the solutions to this are wiggly sine curves. And when I do the Euler approximation, I'm taking like a tangent to this guy going up here and then like doing it again, right? So like I'm basically always kind of doomed to overshoot this guy when it switches direction. Cool. That's not a great cartoon picture, but does that make sense to everybody? Like basically the sine curves down, the line's gonna always overshoot, and it's gonna do it again when the sine curves up at the other side. Okay, so takeaway message of the day. Let's see. Always be careful when discretizing ODEs. Don't trust anybody. Don't trust your simulator. Don't trust me. Sanity check. So what do you guys think? Like if I hand you a simulator, like what are good things to sanity check this kind of stuff? To like, can you trust it? Anyone have thoughts? What would you do? Yeah.
Discrete energy.
Yeah, that's a classic one. That's very good. Anybody else have thoughts?
I have another question.
Yeah.
So why is it tending to one, the earlier part? Shouldn't it be tending to zero because it's marginally stable in ideal case?
Oh, sorry. No, I'm saying that here, this thing only approaches marginal stability, like modulus 1, in the limit as the time step goes to 0. That was that plot. Let's put this back up. This plot, right? So this is the modulus of the eigenvalues plotted versus h. So this is h on the bottom, time step, and then this is that eigenvalue, right? And maybe marginal stability is h equals 1, or not h, sorry, eigenvalue is 1, right? Which is over here. So what's happening is this, this thing's approaching that marginal stable, eigenvalue modulus 1 in the limit as h goes to 0. So that's what I'm saying. Does that make sense?
Okay.
So yeah, you're right. You want the eigenvalue to go to 1 here. You want it to be 1, right? That means it's oscillating. And I'm saying it only gets there in the limit as h goes to 0. So with Euler integration, for any finite h bigger than 0, which is what you need to simulate it, it's going to blow up no matter what. It's just a matter of how many time steps before it blows up. Yeah, cool. Is that everybody else? Okay, so sanity checking. Good things to do. Yeah. So yeah, check energy. Another one would be like momentum, right? So basically, like, if you check energy, right, if it's a conservative system, that should stay pretty much constant. If it's got, if it's a damp system, that should decrease, et cetera, right? Basically, try looking at these kind of quantities and like qualitatively, what should they be doing? And then what do they actually do in the numerical simulation? And you'll find that very, very often the simulators do the wrong thing. Things go in the wrong direction. And that's something you really want to be careful about. Like, you want to make sure your results are qualitatively correct. Like, and if it's damped, energy should be going down in the simulator, basically. And then the main one is there's basically never a good reason to use forward Euler integration. It's super common. It's frustratingly common in robotics and like RL, blah, 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 OpenAI gym kind of stuff. But there's really no good reason for this. It's basically just laziness, or you don't know any better. And I'm telling you about it now, so you know better now. So don't do it. If you do this on your project, I'll be very mad at you. Yeah. Okay, so
if your simulator is based on forward Euler integration.
so like you can read the docs, or like just try this kind of stuff, right? Do these sanity check exercises, simulate a pendulum, what happens? That kind of thing, right? But yeah, like most of these, you can read the docs and understand what they're doing to some extent under the hood, or read the papers. Like all the like Bullet, Mujoko, these things all have good docs, and often there's options for what kind of integrator you use in the simulator options. Okay, so what should you do instead? Now let's talk about that. There's a couple things we'll talk about. So the first one is sort of probably also most of you know about. So still talking about, remember we talked about explicit. We're still talking about explicit integrator or simulator or whatever. We're going to do fourth order Runge-Kutta, which is the sort of industry standard. Who's used RK4? Like most people. Excellent. Basically, this is the first thing you should try in almost all cases. There's definitely places where this barfs. So you shouldn't this is not a blanket, always do this, but it's generally the first thing to try. Okay, so the intuition, sort of like general idea for what's going on with this is, remember with Euler, we were fitting a line, right? Using the derivative at that time step, we fit a line, we go along the line. Does anyone know what RK4 does instead? Anybody? Speak up.
It's a line, goes along the line, recalculates some stuff, goes back along the line, does that. Like
so that's what it looks like, you know, but there's actually a really simple, what it's actually doing. If you like look at, if you derive it, it's fitting a cubic spline. So all those how many function calls are there in RK4? 4. Yeah. So how many points do you need to fit a cubic? So it's literally fitting a cubic spline, and that's how you derive it actually. So yeah, I don't know. That's fun fact. But yeah, it looks super weird. You know, it looks like you're going forward, backward. Really what that's coming from is actually just writing a cubic spline down and trying to fit it with X dots with 4 different values. There's actually, it's not unique. There's actually there's an infinity of RK4 rules you could write down because you can evaluate those points kind of anywhere, right? And still uniquely fit the spline. So there's actually 2 classic RK4s. On the Wikipedia page, but there's an actual infinite number of possible RK4 rules.
And that would just change the weights.
Change the weights and where you evaluate F, right? Because in the standard one, you evaluate it at like XK plus a half, basically twice, and at the initial point and at the end point. You could have, in principle, you could evaluate it anywhere on the interval, right? And like all kinds of different ways. So there's like a sort of whole infinity of possible versions of that. Yeah.
Are there any obvious cases where you'd expect RK to fail?
Yep. It's a long conversation. Basically, there's this notion, this is probably too long to like do here. We can talk after. There's this notion you may have heard of called stiff ODEs. Have you heard of this before? Anybody heard of this idea before? So stiff ODEs like generally corresponds to things with like high stiffness from like a mechanical kind of perspective, like really high stiffness constants or damping constants or whatever in your ODEs somewhere. Basically, yeah, RK4, or in fact, any explicit, this is why we talked about explicit. We're going to talk about implicit integration rules next. Basically, you can prove mathematically that any explicit Runge-Kutta method, any RK method that's explicit like that, will barf on a stiff system. They have certain, there's like this notion of stability that we're kind of talking about here that we're kind of dancing around. You can actually prove that any explicit integrator is not what's called astable. Basically, there's certain stability properties that you can't have an explicit method. And so for a sufficiently stiff system, it's going to barf and blow up on you kind of no matter what. But for relatively benign things, RK4 is like pretty much the go-to. Okay, happy to talk more about that, but I'm going to try to keep trucking here. So yeah, RK4, which many of you seen before and probably used a lot, is just fitting a cubic spline. And so kind of like obviously fitting a cubic spline versus fitting a line, you can get it's much more expressive. You can like have a much better fit to the true underlying solution. So you get much better accuracy. It's also obviously 4x more expensive to evaluate a step with it, right? But it turns out the win in accuracy is way more than 4x. The win is like to the 4th power. So like it turns out the win in terms of accuracy dramatically outweighs the computational cost of like it's basically a constant more expensive, but it's like a high power more accurate, right? So it's always worth it. Okay, so this we're not going to derive this because it's actually a huge pain, but most of you done it before. I'm going to just kind of write the pseudocode for it, and then we'll like do the real code. Basically, looks like this. We'll call this FRK4. That's sort of terrible handwriting. Apologies. So this is kind of a standard way to write this down with these little Ks. Basically, you evaluate F at the current spot. Then you take a half step of Euler, actually. So you do like H over 2 K1. And then you do another half step of Euler, but using K2. And then you do a full step with, this looks super weird and makes no intuitive sense. But where it comes from is basically writing down the spline and then saying, I want to fit the spline kind of thing, right? And then at the end of the day, the actual solution to this is the following. Has anyone seen Simpson's rule by any chance? I don't know what that is. Yeah, does this look like Simpson's rule? It is. It's the same thing, which is, where does Simpson's rule come from? It's evaluating an integral using a cubic spline, which is where this comes from, right? It's the same. The RK4 and Simpson's rule are the same thing. Okay, fun fact. What else we got here? Okay, so now we're gonna go do the pendulum thing again, but with RK4. We'll do the same stuff and like take a critical look. Okay, so here's RK4 that I just wrote down pseudocode for. Yeah, that's what I just wrote, right? Cool. And so we'll do the pendulum simulation thing again. This is just calling it for a bunch of time steps, same kind of stuff. We'll do 10 seconds at 10 hertz, I guess. Same initial conditions as last time, right? That looks pretty good. Hey, how about that? In fact, I can take like even bigger time steps and it's still pretty much rock solid. Anyone want me to try anything?
1,000.
Okay, sure. So it's slightly damped actually, right? But it's pretty good. And if I take like slightly smaller time steps, you know, it'll basically look perfect. So if I went to like, for sure, you know, 100 hertz, totally, you know, stable, right? Like what it's supposed to look like, right? So that's pretty great. So what we're going to do now is I'm not going to handwrite the Jacobian at this like I did last time because it's a lot more annoying. We're going to use forward diff to get the Jacobian. This is what it looks like. It's being on homework 0. It's super straightforward. But yeah, the fact that auto diffing is built into Julia is pretty great. So we're going to do the forward diff thing. And I'm just going to diff through that RK4 step, right? And we'll do the 10 hertz sample rate, say, and we're going to check those eigenvalues. Remember, they're supposed to be 1, right? So look, that matches what we expect out to like, I don't know, 5 decimal places, right? That's pretty good. And you can tell actually from here, it's slightly less than 1. So it's slightly damped actually, which exactly matches the behavior we saw up here, right? So if I put this back to 10 hertz, it's a little damped, right? But it's out at the 5th decimal place. So it only shows up after like 1,000 seconds or whatever, right? Pretty good. Any thoughts, questions? Want me to try anything weird? Yeah.
It's just like floating point slash computational accuracy.
No, they're not. They're coming from the underlying like cubic spline fit, right? So they're not, this isn't like floating point round off error, right? We're way sort of before that. This is actually like associated with this like discretization that I've done to the dynamics, right? The cubic spline fit, the RK4 thing, blah, blah, blah. Yeah. Okay, cool. So that's this. So we're going to make the same eigenvalue plot as a function of h and see what that looks like. This is kind of fun. So check this out. It's supposed to be 1, right? So for sufficiently small h, like around 10 hertz, you know, even up to like, this is like 5 hertz, right? So even 5 hertz is still pretty good. But then you see, as I make the time steps bigger, it starts to become damped, artificially damped. So we're losing energy artificially. And then if I go even bigger, it sort of turns around and now it's adding energy and blowing up like we saw with Euler. That's super weird. And like, I don't know, there'd be no way to kind of predict this from, you know, first principle. So we just try it, but kind of cool. Does anyone want me to try some of these things? We can try, I don't know, we can try 0.4 or something. That might not be so gross. See what happens. Like maybe 10 seconds so it doesn't go insane on us. So yeah, now it's like, but also, you know, we're starting to run up against like Nyquist sampling problems, right? It's super coarse, yeah.
Just curious, does like those transition points have anything to do with the natural frequency of the system?
100%, yeah. So what really matters here is sort of like the ratio of like the natural frequencies to the integrator step size, right? So if I went and changed the length of the pendulum and made the natural frequency of the pendulum like 10 times faster, all of this would get compressed by a factor of 10, right? I'd have to sample 10x faster to capture the dynamics. So it's really, yeah, you nailed it. It's basically what matters here is like the integrator step size relative to the frequency content in the solutions, right? In the dynamics. Yeah, good point.
And then the Nyquist frequency aliasing stuff has to be added onto that RK4 error plot. It's like a separate.
Yeah, so that's actually sort of a separate issue. And it turns out, right, because you're fitting a cubic, you actually can undersample here. So, and still get accurate solutions, right? So you're not actually just, remember, right, I'm actually doing 4 function evaluations per RK step. So I'm actually like, not quite like, if I did this, you know, if I made this H large enough that I wasn't quite at Nyquist, I'm actually still okay here. But you're right, the Nyquist thing is gonna pop up here eventually. And these are kind of separate issues. Okay, yeah, and like, I don't know, I could get this to blow up by going out to like 0.9, maybe. Let's try that. I think let's say 0.95 or something. Yeah, so clearly now it's blowing up. And I'm also like way undersampling also. The solutions look kind of garbagey. But you can imagine if I did cubic interpolation of this and actually like upsampled it, it wouldn't be that bad. It's still kind of like sane. We're not quite at like Nyquist badness, right? Okay, any questions about this? Anyone want to try anything else weird? This is kind of fun. I think this is cool. So yeah, basically it's pretty easy to make these sort of plots. And like the message is, you know, obviously there's this whole, like, you want to take reasonably small time steps. If your time steps are huge, we all know bad things are going to happen. But there's also this sort of discretization error thing that's a little more like insidious. That's a function of the exact way you're discretizing the dynamics. And different Runge-Kutta rules will have different behavior in this kind of setting. And generally, you know, everything's cool when the limit is h goes to 0, but we can't simulate if h goes to 0. So we got to pick something finite. And here, you know, you're good for a pretty good range of h's with RK4. Eventually, it's going to start to do weird stuff. So you always have to worry about this. Okay, cool. What's this? Yeah, we're not going to do that yet. More to come. Okay, cool. Let's keep trucking. Hopefully my iPad didn't die. Okay, yay. It's still alive. Okay, so yeah, a couple of takeaways. First one, the accuracy, I just said this, but you'll just have to trust. You can try this yourself. You should try it yourself. Shouldn't believe me, right? I'm not. The accuracy win here is sort of way outweighs the additional computational cost. I mean, that should have been kind of obvious from those plots, right? Like it's way more accurate. Even if you took like 4x the time step, you know, size versus Euler, so then the computation cost would be the same, right? You get way better accuracy with this. Let's see what else. Yeah, so and then again, this is like a, you know, reasonably sophisticated integrator, right? And even here, weird stuff happens as a function of the step size if I take bigger steps and stuff. So even with fancy integrators, you can't trust them, and you should always kind of be a little bit wary. So always do some sanity checking. Okay, cool. Any questions about any of that? Good. All right. So the next sort of like thing to talk about then is those were explicit. We're not going to talk about implicit discretizations, implicit form, whatever you want to call this. So here, what this looks like now is it's an implicit function, right, rather than an explicit function. So now this FD looks like xk plus 1 xk uk equals 0. So maybe it makes more sense to make a concrete example of this to explain it. So the simplest version of this is called implicit Euler. It looks just like explicit Euler that we already saw, except the f is evaluated at xk plus 1 instead of xk. So it's called implicit Euler, sometimes called backward Euler. So let's see. Yeah, and the main thing is, right, this is at the future time, which is kind of weird. So anyone know how we actually do this in practice? Yeah, let's think. You know? Yeah, it's a root finding problem. So I make a guess at xk plus 1. I know xk, I know uk because that's what I'm doing to the system right now. So I plug those in and then I take a guess at xk plus 1, and the simple sane guess is just xk plus 1 as equals xk as the initial guess. You plug all those in to this equation, move everything to the left-hand side, right? It's not going to be 0. So now you just solve a root finding problem in xk plus 1 until you drive the error to 0. And now you've got xk plus 1. That's how you actually do it, right? Okay, so let's do that story. So do this. right? We move all the stuff that I just wrote over. So it looks like this. And then we solve a root finding problem. That's pretty terrible. For x equals 1. So we're going to talk more about this next week when we talk about optimization. So probably a lot of you know how to do this. So we'll save it for next week. So what we're going to do is I'll just do it and I'll show you the code. And then next week, we'll talk about how to do root finding. Okay, so here it is. Backward Euler. Yeah. This is. And let's plot the thing. So this is like 100 Hertz. Let's do, I'll do 100 Hertz and see what happens. What's happening? What's going on? Thoughts? So first, just the obvious thing is that it's damped, right? It's losing energy, which again, it's not supposed to do, right? It's supposed to be constant. So here, like the important message is this has the exact opposite energy behavior of explicit Euler. So explicit Euler, you're always overshooting because you're evaluating it at the xk, and you get this energy blow up. It turns out with this guy, the implicit or backward Euler, you're always evaluating it at xk plus 1. You're always undershooting the true solution, and so therefore you're always losing energy. You're always like, you get this artificial damping effect. And again, just like the last case we saw, it doesn't matter how big, how much I crank the time steps down. Like if I go out long enough, the same behavior is there, right? Kind of interesting. Although, yeah, from a practical perspective, if I'm trying to make a simulator that doesn't look stupid, this behavior is preferable in a lot of ways to the blow up behavior, right? So it turns out that this implicit or backward Euler is actually, in spite of how seemingly dumb it is, and the fact that it has this pretty nasty, damping behavior, this is actually super common. Like most of the robotics simulators do this. So the default integrator in Mujoko is this. Default integrator in PyBullet is this. It's really, really common. So beware. Yeah.
So this is the exact opposite in the error. You keep running both of them and then average them to get.
That's not a bad idea. You're on the right track to something cool. So actually that works. What you just said, it turns out if you do that out, what you get is something called the implicit midpoint rule, which is actually been on one of your homeworks. And it turns out it does exactly what you expect. So good intuition. It's a very good idea. Yes, that does work out. It turns out. You guys are really sharp. You guys are like, yeah, I like it. Okay, so cool. That was interesting. Where did this go? Let me get rid of this. We'll write down some stuff. Okay, so what did we see this time? Opposite energy behavior. Here, right, discretization adds damping. And yeah, like I just said out loud, this is unphysical, obviously, and wrong. But if you're running a simulator, this looks sort of benign. Like if you're doing graphics, right, you're playing a video game, this is benign, and your video game character will still kind of look reasonable. Whereas the blow up behavior will look stupid and make your whole thing crash and be bad, right? So basically, like this has been historically the preferred simple integrator for things like video game engines. Many of the robotic simulators, which historically have grown out of video game engines, which is maybe not a great thing. Yeah. So you have probably used this before, even if you didn't know it, if you've used any stock robotic simulator.
Is the directionality on the blow up always the same for like periodic motion. Like, so the forward Euler is always gonna blow up, and backward Euler is always gonna damp.
Yeah, it pretty much is. Yeah. So it turns out this is a general property of like oscillatory motion with either of these integrators. And cartoon picture is forward Euler always overshoots an oscillatory solution, and backward Euler always undershoots an oscillatory solution because they're fitting lines, right? And you can like prove this by looking at the next term in the Taylor expansion. You know, like look at the line fitting. Basically, like these things are like kind of secants, right? Let's see. So basically, the reason people like this and why it's used in all these simulators is that this, you know, the damping behavior means it's kind of always stable. So it means you can take big time steps in the simulator and run the simulators really fast, and it's cheap and all this good stuff. Even if it's unphysical, the kind of unphysical behavior here is like more benign, right? So yeah, very common in sort of low fidelity simulators in graphics, game engines, blah, 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 robotics. Okay, cool. What else? So some more takeaway messages. Implicit methods in general are, you know, sort of, this is a very heuristic-y, hand-wavy, you know, story so far, but these are often more stable than explicit methods. And there's a much more theoretically grounded version of the story where basically explicit methods can never be stable all the time. You can prove this, whereas implicit methods can. In fact, you can design implicit methods that provably always achieve like the correct energy behavior, which is cool. Like you can make these always do the qualitatively right thing from an energy perspective. More to come on homework 1.
Why did they call them implicit and explicit? Like, what's it?
Yeah, so do you know about implicit versus explicit functions from math? So an explicit function is y equals f of x. An implicit function is f of x comma y equals 0. That's it. So it's just that, right? So basically the implicit ones are implicit functions of the state, right? The explicit one is an x plus 1 is an explicit function of the current state, right? That's it. So basically the implicit versions, you have to solve a root finding problem to get the next step because it's buried inside this nonlinear function. Yeah. So implicit ones are more computationally expensive to run also, right? Yeah.
By stable, so you mean it's more like the your simulation result will not blow up?
Yep.
Like or it's like more accurate?
No, I mean, not accurate at all, right? It's qualitative, it's obviously not accurate, right? It's doing qualitatively the wrong thing, but it's not blowing up. Yeah. So stability, I mean, very much this idea that the it's decaying towards 0, right? It's damped, it's not going to blow up. I mean, stable in the exact sense we've been talking about the last couple of lectures, right? Eigenvalues less than 1, this kind of thing, right? Does that make sense? Yeah, it doesn't mean more accurate. Okay. Cool. Okay, so yeah, a couple notes on this though that aren't maybe obvious yet. For forward simulation, this should be maybe a little obvious. The implicit stuff is more expensive. In general. But for a lot of control algorithms, specifically like direct methods or collocation methods, which you may have heard of, it turns out just the way those things work and the way they're set up, the implicit method is free and doesn't actually cost more. And so for a lot of these control methods we're going to talk about later, the implicit methods are preferred because they have these nice stability properties and they are not more expensive in these algorithms, it turns out. So that's kind of why we're talking about them, and these will come back later. Plus, they're also just common in general. So that's kind of fun. Okay, so in the last few minutes before we have to leave, we're going to talk about one last kind of little topic that will be kind of important for us. So we talked about discretizing dynamics and discretizing state trajectories, right? With like piecewise linear or cubic splines, right? With these RK methods. Now we're going to talk about discretizing controls, which is a little different, it turns out. So yeah. Also have to do U of t. Okay, so the simplest option is called a zero order hold. So this literally means UK equals UT equals UK for T basically between TK and TK plus 1. So this is called zero order hold. And the cartoon picture of this is the following. So I have like T, and I just do this kind of thing. Make sense? So it's piecewise constant. And at the next time step, I just stick it at whatever the next value is, and it just hold it over the time interval, right? Super easy, super straightforward. This is really, really common. In fact, in pretty much all actual on hardware implementations, this is what is actually happening at the lowest level. You have some, DAC or whatever that's like taking this, signal from the computer and like and actually spitting it out as a voltage on whatever or current in your motors. For the most part, those are doing this at the lowest level at whatever, hundreds of hertz or kilohertz rates. So and it's also just easy to implement, right? But when we're doing, say, offline optimization and this kind of thing, if I'm trying to capture some wiggly continuous signal accurately, I have to take a lot of sample points. Like I have to take really small time steps to get a good approximation of my continuous signal with a zero order hold, right? So that's kind of the downside and why we maybe want to do other things. Basically, we may want to do other things because it'll let us take bigger time steps in our simulation or in our solver for our optimal control stuff. So, and by the way, the lingo in controls for like time step very often is not point. I don't know if anyone's heard this, but when I say not point, I mean basically the discrete time steps. I think that terminology comes from splines, like the not points are the control points right on the spline or whatever. Okay, so then like another option, which is fancier, but I'm going to caveat this with possibly better option, is what's called a zero order hold. So this one is just linear interpolation instead of hold it constant. So mathematically it looks like this. We're going to basically take, UK plus 1 minus UK over H times T minus TK. So this is called first order hold. And the cartoon picture is something like this. So maybe I start here, right? I go like this. You get the idea. So the reason you might do this, right, is this is now, kind of interpolating maybe a little better, and we might be able to approximate a continuous U of t with fewer not points like this, right? But, oh yeah, I guess a couple other comments, right? This is basically, almost no extra work over the zero order hold. So, you know, computationally pretty easy also. And this is actually very common. As just one example, the classic direct collocation method, which we'll talk about later, uses this. So let's say, so yeah, and I guess the sort of other options that you might think about, like the obvious game to play here, which is kind of the one we played with the state, right, is you can keep doing this, right? I went from 0 to whole to first order linear interpolation. I can do arbitrary high order spline interpolation on these guys. And this has been done. There's algorithms that do this. So you can do it. And you would hope, right, that that would give you some nice advantage where you can take fewer and fewer knot points with high orders, which kind of does plan out with our Runge-Kutta methods, right? We said RK4 with the cubic splines is dramatically better than Euler, which is doing the linear thing. But there's a big but here. So with the states, they're generally these smooth things, right? In most cases, modulo like contact interactions with impacts or whatever. So it makes sense to use a nice high order smooth polynomials for that. But controls, it turns out, in many, many applications are just not smooth. It's very, very common to have so-called bang-bang solutions where you're basically railing up against your torque limits and then like railing against your torque limits the other way, right? Full gas, full brakes, like that is very common in control. So in those situations, the solutions, the U of t, are not smooth. So trying to fit a polynomial to them, a very high order smooth polynomial, doesn't really work. You get like the Runge phenomena kind of stuff, this kind of stuff happens. So it turns out that because of just the things you're trying to approximate are generally kind of gross and non-smooth, it's just not worth it. And so we usually use 0 order hold and first order hold in most practical applications. There are exceptions to the rule, like in aerospace applications where you have like continuous low thrust or whatever. This game does work out favorably, and maybe it does make sense there to use like, people use like 8th order polynomials for things there, but in a lot of robotics applications, it sort of doesn't make any sense. So that, I think that's basically it for the day. I'm going to write this down, but yeah, I'll hang out for questions, but we're kind of done for the day. Basically hit the time in spite of the technical difficulties. So hooray.